Okay, hello everybody. Welcome to the TrustML Young Scientist Seminars. So my name is Masashi Sugiyama. So I'm Director of Riken Center for AIP. And this is a seminar series. And actually in January and February, we had a series of seminars and we had 12 speakers. So this is the first talk of the second round. So in March and April. So today, we will have a great speaker. So our guest speaker is Kfir Levi from Technion, Israel. So today he will be talking about Beyond SGD, Efficient Learning with Non-IID Data. So the title sounds very interesting and I'm looking forward to your talk. Okay, then Kfir, can you start your talk?
Thanks a lot, Masashi and Jingfeng. Let's start. Before I start, just feel free to ask any questions you have during the talk. I'll be happy to answer any questions. Okay, so one of the most basic concepts in machine learning is that we learn from data. And one of the most common assumptions that we make in the classical models about data is that the data points are IID, meaning that they are independent and they are identically distributed. However, in many interesting cases, this IID assumption actually does not hold. One interesting case is when our data has a temporal structure. For example, the price of a stock, or if we're trying to forecast the weather, then in this case, the data does have dependence, right? The weather today does depend on the weather yesterday and the days before. Another interesting case where this assumption is violated is when our data is actually contaminated. For example, assume that we get our information from some sensor and this sensor is malfunctioning, or the communication between us and this sensor has some has an interruption, then our data is contaminated. And it might be also contaminated by an adversary that intentionally contaminates our data. Another example is when the data that we receive actually depends on our algorithmic choices. For example, in reinforcement learning, right, you have an agent that interacts with the environment, and the feedback, and actually the data that the agent receives, depends on the algorithmic choices of this agent. Another example is when we have multi-learner or multi-agent settings, and the actions of one agent actually affects the behavior of the other agents, and therefore the feedback that this learner or agent receives. So today I'm going to talk about two cases where we'd like to learn when our data is not IID. The first case is when we would like to solve linear regression problems, assuming that our data was contaminated. And the second case that I will discuss is when we would like to learn from a Markovian data source. A Markovian data source captures very well temporal data structures. So hopefully you have time for both, but in the worst case, we'll do the first and shortly talk about the second. And what I'm going to show you, I'm going to show that we have provable algorithms for these problems that are as simple and efficient as the baseline algorithm that we usually use in machine learning, which is the stochastic gradient descent algorithm. And we are also going to see that these algorithms actually implicitly adapt to the structure of these problems. Okay, so let's start with the first topic about how to solve linear regression with contaminated data. And this is based on a joint work with my student Tom Norman, and also with Nir Weinberger, which is also a staff member here in the Technion. Okay, so the model in this case is the following. We have a learner that receives a set of labeled training samples, and we assume a specific relation between the labels and the features. We assume that the labels are linear, noisy functions of the features. And more concretely, we assume that each label is yi is an inner product between its feature xi and some weight vector, which we denote by w star, and this weight vector is unknown to the learner, plus some measurement noise epsilon I, which is zero mean. So this is the standard model, but actually we're going to discuss a more complex model in which an adversary is allowed to contaminate an alpha fraction of the samples, right? And this contamination is in the form of an additive perturbation that he adds to the labels, and we denote this perturbation here by bi. So we don't have actually any constraints about bi. It can be unbounded. It doesn't have to be zero mean. The only thing that we have, the only constraint that we have here is that the adversary can only contaminate an alpha fraction of the samples. Well, alpha can be 1%, 50%, and even 90%. Okay, so the setting is the following. We have a learner that receives T training samples from this contaminated distribution. So the alpha here denotes the distribution of contaminated samples. And this learner should output a solution or a prediction W bar for the optimal solution W star. And the goal of the learner is actually to generalize with respect to the square loss that is defined on the clean distribution of the data that we denote here by D. Okay, so the learner would like to has an access to contaminated data, but he would like to ensure guarantees with respect to the true clean data. Okay, so the goal of the learner is this, and we measure the performance of the learner using the generalization error, which is defined here. Okay, so what can we do in this case? So the straightforward approach is to say the following. Okay, let's ignore the fact that the data is contaminated and solve this problem using least squares, like standard least squares. And apparently that's a very bad approach because it may completely fail, even if we allow the adversary to contaminate only a single data point. Okay, so this approach is very bad. It fails. So okay, again we can ask, so what can we do in general? And apparently what we can do in general depends on the power that we assume that we let the adversary have. So we can roughly divide into two kinds of adversaries. An adaptive adversary is a powerful adversary, and this kind of adversary may view the whole data set before he chooses his perturbations, his contaminations. And apparently, if we have a learner that has to learn or compete against this kind of adversary, then he cannot, it is known that such a learner cannot ensure an error that is vanishing as the number of samples is increasing. So even if this learner has an access to infinitely many samples, the best thing that he can ensure is to find the solution W that is close to the optimal solution W star up to some a constant factor of square root of alpha. Or alpha, again, is the fraction of points that are contaminated. So this topic of robust regression or robust statistics started in the 60s with the seminal works of Tukey and Huber. And in the last years, it became again very popular. And these works and some other interesting works from 2019 and 2020 have explored and provided non-asymptotic guarantees for this setting. But actually, this kind of adversaries is not the focus of what we're going to discuss today. We are going to focus on weaker adversaries, which are called oblivious adversaries. And these adversaries cannot view the data points before choosing the perturbations, but they have some knowledge. They may know the true distribution of the clean data, and they also may know the value of the optimal solution W star. Okay, and apparently, and surprisingly, it was shown that if you have such an oblivious adversary, you can ensure an error that vanishes as the number of samples, your samples increases, even if the fraction of contamination is greater than 50%. Even if you allow the adversary, to, for example, to contaminate 90% of the samples. So this guarantee was shown, so we can find a solution that is close to W star that goes like 1 over the number of samples that we have, of course, depending on the fraction of contaminated samples. And this is the setting that we are going to focus on today. And again, the work on these problems started in the 60s, and there's been some very interesting works throughout the last years that provided non-asymptotic guarantees, like we see here. Okay, so let's look more closely at these works. And if you look more closely at these works on the oblivious case, you'll see that they are done under some limiting assumptions. So specifically, in all of these works, it is assumed that sigma, the covariance matrix of the features, is positive definite, meaning that its smallest eigenvalue is lower bounded by some quantity rho. And all of these works actually require the knowledge of alpha, what percent of samples were contaminated by the adversary. So also, most of the works makes even more stringent assumptions. They actually assume that the features and the noise are Gaussianly distributed, which is very limiting. And they also assume that the features are centered, meaning that the expectation of the feature vectors is equal to 0. One exception is this very nice paper of Dorsey et al. From 2021, which actually gets rid of this Gaussianity and centered assumptions. So Dorsey provides guarantees without these assumptions, but he actually makes an assumption that weakens the adversary. He assumes that the adversary may only choose symmetric perturbations, in the sense that the probability of the perturbation being z is equal to the probability of the perturbation being equal to minus z. So this is a very strong assumption or weakening of the adversary. And they also make another assumption on the covariance matrix, which they call spreadness, which again limits the generality of their setting. So we're actually investigating this case, the oblivious adversary case. And what we do in our work, we actually get rid of these limiting assumptions, and we provide practical algorithms, which is basically a variant of SGD that provably solves this problem. So we make no assumptions on the adversary, on the perturbations that he is allowed to do. We allow the distribution of the features and the noise to be very general, like coming from a bounded distribution or sub-Gaussian distribution. And we don't make any assumptions on the covariance matrix of the features. Again, if you have any questions, go ahead. So more specifically, in our analysis, we divide into two cases. The first case that we discuss is for general sigma, general covariance matrix. And we show that this case is actually divided into two interesting subcases. The first subcase is when the features are centered, meaning that the expectation of the features is equal to 0. And in this case, we show that we actually can find an algorithm that ensures that the generalization error will go to 0 as the number of samples increases. And this is the first result for the case of general covariance metrics. On the other hand, we show that if the features are non-centered, then we don't have a learning algorithm that is able to provide non-trivial results for this case. The second case that we discuss is when the covariance matrix is positive definite. And in this case, we show that it doesn't matter if the features are centered or not, you can still ensure an error that decreases with the number of samples. It's roughly the same rate of error. When the features are not centered, then we incur another logarithmic factor in the error, but it's not very substantial. Okay, so let's talk about these results, and let's first talk about the negative result or impossibility result that we show. So the example that we have for this impossibility result is very simple. So we take alpha to be equal to half, meaning that the adversary can contaminate 50% of the data, and we let x be equal to 1 with probability 1. So the features are fixed and equal to 1 all the time. So now we look at two models. In the first model, the label is always equal to 1. And in the second model, the label is always equal to -1. Okay, so of course, these models are distinguishable from each other. It's easy to distinguish between them. But now what the adversary will be doing, he will inject noise or perturbation to these models such that after the perturbation, it will be impossible to discriminate between them. Okay, so the adversary is doing a very simple thing. To model number 1, he injects -2, an additive perturbation of -2 with probability half. Otherwise, he does nothing. So after the perturbation, the labels in model 1 are +-1 with equal probability. And similarly, to model number 2, the adversary injects a perturbation of +2 with probability half, and otherwise it doesn't do anything. So actually, after the perturbation, these models, the samples from these models, look exactly the same. They're uniformly distributed between -1 and 1. So actually, any learner cannot distinguish between these models from the contaminated samples, and meaning that we cannot ensure we cannot do learning in this case. Okay, so far for the bad news, and we can now talk about the good news. Okay, so maybe before we talk about the good news, let's discuss why does least squares breaks down. So it's quite well known that least squares breaks down, and the reason that it happens is that the square loss is very sensitive to outliers. Okay, so technically speaking, the reason that the square loss is very sensitive to outliers is since the gradient of the square loss is becoming larger and larger as we go far away from 0. And this gives a lot of power for the adversary, for the outliers. So one very natural way to resolve this issue is to replace with the square loss with a square loss that is more robust, right? And by saying robust, I mean exactly this technical property that for a robust objective, as you go far away from 0, the gradients do not explode. They come to some, they're bounded by some fixed value. So one natural loss that is robust and convex is the L1 loss. And of course, these properties hold for the L1 loss. But another option, which is very popular, is the Huber loss. Now, the Huber loss was suggested by the Swiss statistician Huber in his seminal paper from 1964. And what's special about the Huber loss that it has two very nice guarantees or properties. The first property is that it actually coincides with the square loss in a region of R, of radius R, around 0. And around this region, then the gradient is fixed. The gradient is not exploding, and it's actually equal to R. So actually, for the Huber loss is a parametric loss. We can with a parameter R, and we can choose this parameter R as we wish. Okay, so our approach to handling this robust learning problem is actually to adopt the approach of Huber and use this robust loss as a substitute or the surrogate for the square loss. Okay, so our new objective that we suggest is to minimize the expected Huber loss over the contaminated data set, and we denote this expectation by capital L R of W. Any questions? Let me see if there are any questions.
Can you see the QA box?
Is there any assumption?
No, chat box actually, yeah.
Yeah, I can see it now. Is there any assumption on the magnitude of the adversarial noise? No, it can be unbounded. We don't make any assumptions about it. Okay, so our approach is actually to use this to solve this expected Huber loss problem over the contaminated data. And what we actually show is that for the right choice of this parameter R, we can tie between this LR of W, this robust loss, which is defined over the contaminated data, and between the true square loss, which is denoted here by F of W, that is defined over the clean data that we don't have access to. Right? So actually, one of the main lemmas in our paper is the following relation that says that if the features are centered, then for the right choice of R, this parameter of the Huber loss, then we can show the following inequality. And this inequality is very strong in the sense that it ties between what we have in the left side, which is the generalization loss with respect to the true data that we cannot access, and between, so we can mount this error by some constant times the error on the Huber loss, LR of W, which is defined on the contaminated data that we can access. So this is a very powerful inequality. It's not very complicated to prove it. And actually, this inequality suggests a very nice natural algorithm. Okay, it says that if we want to minimize the true expected loss, it is enough to minimize the Huber loss or by using the contaminated data. And this directly will ensure us guarantees for the true expected loss over the true clean data. Okay, so one way to minimize LR of W is to use, for example, stochastic gradient descent, which appears here. So if you apply stochastic gradient descent on the Huber loss using the contaminated data, it directly translates to a generalization error of 1 over square root of t times 1 minus alpha over the true expected loss. Okay, so that's the first positive result that we discuss. Now the question is how to pick this parameter R, and the answer is very simple. We would like to pick the smallest R such that for any non-contaminated data point, the Huber loss equals to the square loss at this point. Okay, so that's how we should pick R. And specifically, a specific choice of R that satisfies this property is to take R to be 6D plus sigma, where D is a bound on the radius of the optimal solution. So we have to know in advance a bound on the radius of W star, and sigma is a bound on the magnitude of the noise. Okay, we also assume for now that the noises are bounded. Okay, so now we can talk about the case of positive definite covariance. And similarly to a dilemma that we showed before, we can show the following, that if the covariance matrix is positive definite and the features are centered, then for the right choice of R, this parameter, then two good things are happening. The first thing is that this expected Huber loss, LR, is strongly convex with a parameter of y minus alpha times rho. And W star, the optimal solution of the original problem, is the global optimum of LR of W. Okay. So for those who don't know this notion, strong convexity of LR of W means that its Hessian is positive definite, and the smallest eigenvalue of the Hessian is bounded for below by y minus alpha rho. And this strong convexity allows to obtain fast convergence rates to the optimal solution. So basically, if you apply the right version of stochastic gradient descent to LR of W, we can ensure that the distance between the solution of this algorithm between the optimal solution will go, the square distance will go down by a factor of 1 over t, where t is the number of samples that we have. Okay, so this fairly immediate results given the strong convexity and the fact that W star is the optimal solution or the global solution of LR of W. And I just want to tell you that this version of stochastic gradient descent actually requires the knowledge of the strong convexity parameter, and the strong convexity parameter, right, y minus alpha rho, actually depends on alpha, the fraction of points that the adversary perturbs, right? So this version actually requires the knowledge of alpha. We'll talk about it. We'll mention this again later on. Okay, now what happens in the strongly convex case, in a positive definite case, if the features are not centered? So if the features are not centered, then again, we can show that for the right choice of R, LR of W is still strongly convex, but the second property doesn't hold. W star, the optimal solution of the original problem, is not the global minimizer of LR of W. So still, what can we do here? So the solution that we came up with is a very simple solution. Instead of working with the original features, what we should do, we should actually center the features. Okay, how do we center them? We use some of our data, say half of our samples, to get an estimate on the mean of the features. This is denoted here by mu hat. And then what we do, instead of using the original samples, we use the centered samples. So I'll just read this question. So squares is sensitive to corruptions, thus you replace the loss by a less sensitive one, the Huber loss, but now can less sensitive result in a correct result? Since it seems Huber will still be affected by the contaminated data. By correct, I mean the true expected result you showed. Could you please elaborate more? So I don't really understand the question. So I can just repeat what I said before, and hopefully it will be enough. So I agree that the Huber loss is affected by the bad samples, the corrupted samples, but still what we show is that it still converges, at least in the strongly convex case, to the true solution of the original problem with the clean data. In the non-strongly convex case, we show that it gives us good generalization for with respect to the optimal solution of the clean data. Does it answer the question?
Can I continue the question?
Yes,
so
sure.
You had the upper bound, like so. Right hand side was the difference between LR or something like that. But by that you show the convergence, right?
Exactly.
Yeah. So here. Yeah. Then so actually, what was the essence of the Huber loss here? So Huber loss has L1 part and L2 part. So naively, we may think like L1 part is important to be more robust, but because the choice of R is important. So then,
right.
What was the essence here?
the essence of the choice of R. So this is.
Or like, can we have the similar upper bound for the L1 loss?
For the L1 loss, I think not in general case. So there is one work that shows that you can actually get guarantees with the L1 loss, but this is very limited to the case of Gaussian. So this really heavily relies on the Gaussianity of the features and the noise, which we don't assume here.
So then both L1 part and the L2 part are important.
Yes, the L2 part is important to make sure that we have the same loss for the correct samples.
I see.
So the question here, so does the generalization bound converges? The generalization bound shows that we have convergence here. We converge to a good solution with respect to the clean data. Any other questions?
So one naive question I should have asked in the beginning. So your model is to add BI to each sample. So what was the motivation of considering this model?
You mean what's the motivation? So not always does the adversary is actually so if the adversary is malicious, then I agree this model is not so well motivated. But if some error happens, right? If you know there's an error in the communication or error in the sensor, so I think it's reasonable to assume that the perturbations are actually oblivious, are not adversarial.
Okay, and currently, so this is the kind of most general solvable model you have.
Exactly. That's the most general solvable model that we have. If the adversary is actually malicious, then you cannot show convergence, like I said, to arbitrary small error.
Okay, thank you. One more question in QA box. Can you see the QA box?
Yes, I opened it now. Do you consider that the perturbations are generally sparse with alpha fraction of features contaminated? Yeah, we assume that only an alpha fraction of the features are contaminated. Exactly, that's exactly the assumption that we make. But alpha could be greater than 50%. It could be even 90%. Okay, great. Okay, so I'll continue. If you have more questions, again, feel free. Okay, so now in the strongly convex case, when the features are non-centered, then we actually have a problem because we don't have this nice property that W star is the optimum of the robust loss of LR. And the solution that we find for this is, again, very simple. What we should do is just center the features. So we take the original samples and we replace them with centered samples. And the centering we do by estimating the mean of the features, and you can do this on the fly, or you can do, or in the analysis, what we do, we just estimate this based on half of the samples and then run the algorithm for the next half of the samples. But it doesn't mind, even if you do this on the fly, it's fine. And then after we center the features, we just apply stochastic gradient descent to the centered features, to the Huber loss with the centered features, and we can show that it ensures more or less the same rate of convergence to the optimal solution. By the way, the proof is not as easy as in the previous case of centered features, because then it's just straightforward. Here it's a bit more complicated. Okay, so now we can talk a bit about experiments. So we took a data set of samples. We made sure that the problem is that the covariance matrix of the features is positive definite, and the features were not centered. And first, we allowed an adversary to contaminate 1% of the samples. And then we ran our algorithm, which appears here in red, together with a bunch of other versions. And you can see that our algorithm actually converges. And the other versions or the other algorithms that we tried were actually using HDD on the square loss. We're using HDD on the square loss plus centering the features, and using HDD on the Huber loss without centering the features. So what we can see from this experiment is that both of these ingredients are necessary. Both using the Huber loss and centering the features is necessary in order to ensure a convergence. And the same behavior persisted when we allowed the adversary to contaminate 70% of the data. Again, you can see that eventually our algorithm converges, but all the other versions do not show any convergence. So we can actually summarize this part. In the paper, we show also two extensions. We extend to the case where the features and the noise are not bounded by, but we allow the distributions to be sub-Gaussian, and we show the same rates, more or less. The only thing now is that if the features and noise are sub-Gaussian, we have to increase this R parameter by a factor of square root of log t. And we also, if you remember, in the positive definite case, I told you that the learning rate in the algorithm should know alpha, should know the fraction of polluted or contaminated samples, and we extend it to an algorithm that actually doesn't need the knowledge of alpha and still provides the same guarantees. And for future directions, we're trying to see what about other loss functions, and can we also adapt to the other parameters of the problems, like the diameter of W and to sigma, the variance of the noise. So I think it's the good place to take questions for this part. Okay. Kohai asks, could similar results hold for logistic regression with random label noise? That's a good question. Intuitively, I think it does. Intuitively, I think it does, because it seems like one of the most important properties of the Huber loss is that the gradients are bounded. And for logistic regression, right, the loss is bounded. The loss is naturally bounded. So I guess it will work through. But I think technically it will be harder, because like what we do, the square loss is very nice in the sense that if you take expectations of the square loss, then you have right, basically you have first order statistics and second order statistics, and you're done. For the logistic loss, I guess it will be more technical, but I think it's the case. So Hiroki asks, what accounts for the increase in the loss function for other three cases? What accounts for the increase of the loss function for other three cases? What does it mean? Like, I didn't really understand the questions. Okay, maybe we can go back to this later on. And Junia asks, the knowledge of rho is needed? Or rho? Okay, that's a good question. So for the basic version that I showed you, the knowledge of rho is needed because it's related to the strong convexity parameter of the problem, and you have to encode this strong convexity into the algorithm. But for the more advanced algorithm that adapts to alpha, it actually also for free adapts to the value of rho, because we actually are using a method that adapts to the strong convexity of the problem. And the strong convexity is 1 minus alpha rho. So we get it actually for free. I didn't quite understand the question of Hiroki. Maybe you can elaborate on this, or we can take it offline also. I'll be happy to take it offline. Okay.
Just Hiroki said, so the curve in the second last presentation, the experiment.
The experiment. Okay, let's go back to the experiment. So what accounts for the, you talk about the experiments. Okay. The curve in the second last experiment. Okay, so what accounts for the increase in the loss function for other three cases? That's a good question. The answer is that I don't know. That's a good question. It's roughly constant, but I guess I agree there's a small increase. A good question. I actually don't know. We didn't get into this. Yeah, I don't know. That's a very good question. Have to think about it. Any other questions? Masashi, how much time
don't
do you
mind
have?
too much because we're asking a lot of questions. So already,
No, that's
question
perfect.
time
That's
is
perfect.
included. So let's continue.
So maybe like 10 minutes or 12 minutes, something like that. It's fine.
Yeah, so we don't have to really go very quickly. So let's continue.
Okay. So I'll try to be quicker because I don't have a patience to. I guess like I can talk like as much as you want, but I guess it's hard to sit and listen for so long for such a long time. Okay, so I'll tell you maybe briefly about this work. So in this work, we're actually talking about what happens when your data points are not IID, but actually coming from a Markov chain. And this is based on a joint work with my student, Ron Dorfman. Okay, so a Markov chain is a very natural way to model temporal data, like the price of a stock or the weather. And assuming that we have a sequence of data points, Z1, Z2, that arrives one after another, what we're doing here, we are assuming that the Markov property holds. And Markov means that given the present, the future is independent of the past samples, right? And in this work, we also make some technical assumptions about the Markov chains of our data. And basically, this technical assumption means that we have some limiting distribution or stationary distribution denoted here by D, that after enough time, the distribution of the data actually converges to this stationary distribution. Okay, so now one very important property of Markov chains that will be important to what we're discussing today is the mixing time of the Markov chain. So roughly speaking, the mixing time of a chain, denoted here by tau mix, is the number of samples that we have to wait until two samples are effectively independent of each other. Okay, so for example, if these white squares are the samples of the Markov chain, and we take this comb of samples that are separated tau mix from each other, then these blue samples are effectively independent of each other. Okay, so I will not get into all of the technical details, but just keep in mind that if we wait for tau mix between samples, then they're effectively independent. And that's the formal definition. Let's not get into the formal definition. And now we can present our setting. What we like to do, we have a learner that receives a training set of samples that arrive from some Markov chain, as this learner should output a solution, W bar, and the goal of the learner is to do well, to find a solution that does well with respect to the stationary distribution of this Markov chain. Okay, so the learner would like to generalize well with respect to the stationary distribution of the chain, which is very natural, right? That's the natural comparator or natural distribution to relate to. And again, our performance measure for the learner is the generalization error with respect to this stationary distribution. So now, like the immediate question to ask is why just not use the standard algorithm that we're using, which is stochastic gradient descent. So at every time, just draw a sample from the Markov chain, design an estimate for the gradient based on this sample. That's what we see here in green. That's the estimate, and then make a gradient update using this estimate. So that's what we're doing usually in machine learning. And the reason that this problem is challenging is because the following fact, these gradient estimates, in the case of dependent data are no longer unbiased. They actually have a bias, in contrast to the IID case where these gradients are unbiased. Okay, so that's the challenge that we're facing. And due to this challenge, if we apply the standard version of SGD to this problem, then we actually surprisingly get guarantees. We get guarantees for generalization error, but these guarantees are suboptimal. So we can show that the generalization error will behave like the mixing time divided by the square root of the number of samples. While the optimal error that you can achieve in this setting is proportional to the square root of the mixing time rather than the mixing time itself. So we have a square root of mixing time gap between what we can achieve with the standard method and the optimal method, and this gap might be substantial. So there are some Markov chains for which the mixing time is proportional to the number of states that this chain can take, and this might be huge. Okay, let's give some intuition behind this optimality, behind why this error is optimal. So the intuition is very simple. Assume that we have T samples from a Markov chain with a mixing time of tau mix. So the number of effective samples that we have is T divided by tau mix. You can take only this comb of blue points, right? So basically the optimal error is 1 over the square root of the number of effective samples, which is T divided by tau mix. So that's the intuition behind it. And now let's talk about how to obtain this optimal error. So there are at least three ways how to obtain this optimal error. You can actually obtain it very simply. The first approach is to use stochastic gradient descent with a learning rate that decreases, that is shrinked by a factor of 1 over the square root of the mixing time. Another approach is just to take use SGD, but only on samples which are separated by mixing time from each other, which are effectively independent from each other. And there are other techniques. I don't want to get into them, but note that this applying these optimal methods requires the knowledge of the mixing time. You have to know this value in advance. And the question that we ask in this work is, can we find an optimal method that does not know this mixing time, that implicitly adapts to the mixing time? So one natural idea that you can suggest in this context is to say the following: okay, just let's estimate the mixing time, and then use this estimate in one of these algorithms. But apparently, this is not such a good idea, because estimating the mixing time might be a very hard or a very computationally hard task, right? So estimate the mixing time might be even costlier than doing the optimization process. Another idea is to do a grid search for the mixing time, meaning that by grid search you apply you apply one of the previous algorithms with various values of the mixing time to the data set, and then you take the best result. But this requires at least log T runs, and it means that you have to save the data set. It's not an online, you cannot do it online. You have to save the data and then apply versions of your algorithm to this data with different parameters. And our approach is just in one run to obtain the optimal rate and implicitly adapt to the mixing time. That's what we aim to do. So let me talk with you a bit about the challenge and the technique, and then we can finish. Okay, so the challenge that we talked about is basically that the gradient GT, the gradient that we have, is biased, right? This bias, it has a bias of O of 1. It also has a variance of O of 1, but we usually are fine with variance, right? The standard SGD works with gradient estimates which have variance, but the bias is the actual issue here. So we actually would like the bias to be of the order of the error that we try to obtain. So what we can hope to do is to maybe have some machinery to take these bias gradients and translate them into gradients with small bias. So a very simple machinery to do this is to use a mini batch. So if you use a mini batch of T samples, right, then you can devise a gradient estimate that we call here G tilde, which has a small bias, a bias of the square root of the mixing times by T, which is of the order of the error that we aim to get. And if you do this, you also get a benefit that the variance of this estimate also decreases, even though we were fine with the previous variance that we had before. So this is nice, but the problem with this estimator is that it's too costly. You have to spend T samples to get one estimate of this G tilde. So what can we do? We can use the weapon of wishful thinking. And what we can do is that we can hope that there would be a cheap way using few samples to trade off the bias and the variance. So the bias of the original estimate is O of 1, and we would like to get a bias of the square root of tau mix divided by T, because that's the optimal error that we aim to get. But we're willing to compromise. We're willing to suffer an increase in the variance. And apparently, it's if the variance is increasing up to the value of a mixing time, then it's fine. So we would like to have, so we wish we could have a way to trade off the bias to a small bias and pay by increasing the variance by a factor of the mixing time. If we would have a way to do so, then what we could do is to use a method that is adaptive to the variance. Right? Because now we transfer the problem from the bias to the variance, but now we have to cope with this problem of the variance. But in this case, what we can do, we can use first order methods, which adapt to the variance. So one example of such a method is Adagrad. So Adagrad, the aptitude rule of Adagrad looks the same as the aptitude rule of gradient descent. The only thing is that the learning rate in Adagrad is very special, right? It's inversely proportional to the sum of square gradients that we've seen so far. And apparently Adagrad is a method that adapts to the variance of the problem. So this is the guarantee of Adagrad. The generalization error of Adagrad is related to the bias and the square root of sum of variances. And if we put this wishful thinking properties of the gradient estimate that we hope to achieve, then we'll get the optimal rate. So now we have to make this wishful thinking work. We want to understand how can we convert this kind of gradients with a bias and variance of O1 to a gradient estimate with a small bias, but with a larger variance. And apparently there is a recent technique called multi-level Monte Carlo that allows us to do this translation or trade-off with a few samples, with only logarithmically a number of samples. So I see that we actually ran out of time, so I'll just tell you in a high level. So multi-level Monte Carlo gradient estimation is a fairly recent technique in machine learning. Actually, this technique came from physics and from people who try to solve PDEs, but it was recently adopted among the machine learning people, and it's found use in many applications. And what we show here is that actually useful in the context of learning with dependent data. I will not get into this describing this estimate. It has some nice form of an estimate. I guess if you would have more time, then I could talk about it more. But anyways, there is a very nice way to build this kind of estimates. So basically, our overall scheme is the following. We have the standard gradients. We translate them to gradients with the properties that we would like using multi-level Monte Carlo. And this translation logarithmic number of samples, and then we use undergrad to get our solution. And undergrad implicitly adapts to the variance of these estimates. So I'll not talk about the experiment, so I can conclude. So what I've showed you so far applies to stochastic convex optimization, to convex problems, but we actually extend this also to non-convex problems with Markovian data, and we also give an extension to TD learning in RL. And one of the natural future directions is to find applications in control and RL to this kind of combination between multi-level Monte Carlo estimates and between adaptive methods. Okay, so I'm ready to take questions if you have any.
Okay, thank you very much for the very nice talk. So we can still have a few questions, even for the first part or second part. So you may speak or you may write it in QA box. One question in the chat.
Do you think how it is difficult to extend the results to the infinite or continuous state space? That's a good question. We deliberately stayed far. Didn't get into the case of infinitely many states because I think the measure theory and probability theory is more complicated. Basically, I think it doesn't matter so much as long. I think that the important property is that this Markov chain has a stationary distribution, and you can define a mixing time for this stationary distribution. So as long as this holds, I think it doesn't matter if you have a continuous state space or discrete state space for the samples. So Liu asked, I hope that the reference of the slide would be given.
If you are fine, so please provide us the presentation
the slide. Sure, of course.
I have a question. So I'm not familiar with the multi-level Monte Carlo methods, but doesn't it increase kind of randomness of the algorithm?
Yes, it increases, right? We actually show that. But we will find this, right? We wanted to translate, right? The variance was O of 1, and now the variance increases by a factor of tau mix.
So this is an informal question, but often, so even if the performance is guaranteed theoretically, this kind of highly random algorithm does not work well in practice. Do you have any experience like that?
That's a very good question. So eventually we made it work in practice, but I cannot say it's ideal. So you have a good intuition because actually the variance is really a big problem in practice. And we're trying to currently actually understand how heuristically, or maybe not heuristically, try to address this thing in practice to make it be actually a very practical algorithm, but in practice, it's not perfect. It's far from being.
Well, what happens if the dimension is not so high? Does it work well?
We didn't try. I think we tried in. Anyways, I think we tried only in 50 dimensions or so. I'm not sure, but we didn't try in very low dimensions. I think that the problem is not the dimension, but rather the variance, like you said.
I see.
The variance explodes. The variance is very big.
And one more question in the QA box.
Yes. How is the robustness to adversarial attack between Huber loss and adversarial training loss? Are they comparable or any difference? How is the robustness? So I think the trouble is that in adversarial attacks, usually you cannot think of the adversary as being oblivious. I think it's actually an adaptive adversary, right? Because you design the attack per sample. So I think all of what we talked about in this context breaks down. I think it doesn't apply generally to adversarial attacks. But I'm actually also not very well, I don't really know very well what is adversarial training loss. So I guess it's kind of a robust training loss that people use in to defend against adversarial attacks.
Yeah, the min-max one, I think.
The min-max one. Yeah, out of the box, I think they're not comparable because, again, I guess that the min-max thing will defend against right, it's trying actually to defend against an adaptive adversary, right? Because the attacks are the attackers know the features. So I think it's incomparable. I don't think the Huber loss will work well comparably to the min-max for this kind of problems.
Maybe this is like a very good question because there are many different formulations of adversarial attacks, and your method is good for, of course, your model, and then min-max one is good for that formulation. But in practice, we don't know what kind of adversaries we will have. Then what would be the best, choice in practice? Have you ever thought about that kind of approach?
No, actually, that's a good direction. No, we didn't think about it, but it might be useful. That's a very good direction to think about.
And one more question from Junya.
Yeah, I see. I asked this because I wonder the total variation distance considered in the mixing time might be not so much useful in the continuous case. This is not a question. Thanks. Okay, it's not a question. Okay.
Okay, so then thank you very much for the great talk. So join me to thank him. So actually the real purpose of having a seminar today is not to really just have a talk, but to have a future collaboration possibility. So I think today, so from our side, I think there are many like online learning and stochastic optimization people here. I think they are very much interested in your talk, and maybe we are having something in common. So hope that we can keep continuing, and the real fruit out of this talk is to find the next topic to work together.
Certainly.
Yeah. So hope that, so we can't really have a physical chat after the talk, but let's continue more detailed discussion offline by email.
Cool. I'll be happy to talk, and thank you for participating and asking questions.
Okay, so then thank you very much. So that's all for today.
Bye, guys.
Okay, bye-bye, Phil.